We are currently located in the Museum of Extraterrestrial Matter at the Vernadsky Institute of Geochemistry and Analytical Chemistry. This is the only museum in Russia specifically dedicated to materials of cosmic origin. It is situated within our institute because research on extraterrestrial substances has been conducted here for decades. The institute serves as an expert center in this field and houses the largest meteorite collection in Russia. Additionally, it holds the entirety of the lunar soil brought back by the Soviet Luna automatic spacecraft missions. The exhibition is further enriched by a range of scientific instruments developed by one of our institute's laboratories in collaboration with space industry enterprises. These instruments represent the history of planetary exploration of Mars, Venus, and the Moon over the past 30 years. All specimens on display are authentic natural samples. As you can see on the pedestal, both large and small meteorites are presented, along with smaller vitrines showcasing additional samples. The exhibition also features artistic renderings by eyewitnesses. Historically, capturing a meteorite fall on camera was virtually impossible, given the unpredictable nature of such events. These eyewitness illustrations serve to document and convey the dramatic nature of meteorite falls. Before you are some of the most visually striking meteorites in our collection. Displayed on stands are well-preserved specimens with near-perfect aerodynamic shapes. One such example is the Karakol stone meteorite, which exhibits a classic conical form. Another is the Nikolaevka meteorite, also stone, with a less symmetrical conical shape. We also present the Repeev Khutor iron meteorite, notable for its aerodynamic features. Below, you can observe fragments from the Pervomaisky meteorite shower, which occurred in the Vladimir region in 1933. Among the oldest specimens in the collection is the Timochin meteorite, an early example with a unique fragmentary morphology. To the untrained eye, it may resemble a crystal, but it is in fact a fine-grained polycrystalline rock, an unusual and intriguing form. At the center of the hall stands one of the most renowned and massive meteorites ever recovered in Russia, the Sikhote-Alin meteorite, represented here by a specimen from the event. It is an iron meteorite that fell as a meteorite shower. Notably, we also feature a painting by artist Pyotr Medvedev, who was a direct eyewitness to this extraordinary event. Unaware of the impending cosmic spectacle, Medvedev had gone out to sketch a winter landscape on February 12, 1947, when he witnessed one of the most significant meteorite falls in recorded history, certainly the most dramatic observed fall in the last 250 years. An estimated 400 to 500 individuals observed this event from various locations. A bright fireball was visible over distances spanning tens to hundreds of kilometers. Eyewitnesses reported the fragmentation of the meteoroid as luminous fragments separated from the main body. The presence of a smoke trail indicated that a substantial mass had penetrated the atmosphere and reached the Earth's surface. The total recovered mass of the Sikhote-Alin meteorite is estimated at approximately 100 metric tons. It exhibited all the physical phenomena typical of large meteorite falls, including intense fragmentation. This was the largest recorded meteorite shower in modern times, with tens of thousands of individual fragments falling to Earth. The most massive pieces did not decelerate entirely and impacted solid bedrock, forming over 100 craters, each with a diameter of more than 1 meter. The largest crater measured 26 meters in diameter and 6 meters deep. Tree fragments were found over a kilometer away from the impact site. Such a fall qualifies as a catastrophic event, and it was accompanied by a range of acoustic phenomena reminiscent of thunder or artillery fire, along with hissing and whistling sounds. The Sikhote-Alin meteorite fall remains one of the most spectacular meteorite events to have occurred on Russian territory. There is a wide distribution in the masses of individual fragments. The specimens displayed here weigh 65 kilograms, 55 kilograms, and 90 kilograms, respectively. In the display case, you will also find smaller fragments down to the milligram scale, micrometeorites, which are typically found in the tail of the strewn field. The largest known fragment of the Sikhote-Alin meteorite weighs 1,700 kilograms and is housed in another section of the Fersman Mineralogical Museum. This extraordinary event provided humanity with a rare, first-hand observation of crater formation by meteorite impact. It was an exceptional meteorite shower, with a strewn field measuring approximately 12 kilometers in length and 2 kilometers in width at its widest point. The second largest meteorite fall on Russian territory is the Tsarev meteorite, which fell near Volgograd in the Volgograd region, likely in 1922. More than 80 fragments have been found in local fields. It is possible that the fall was witnessed at the time, even from neighboring provinces, as reports indicated a significant meteorite event. However, the meteorite itself was not recovered immediately. It was only discovered 50 years later during agricultural work, when the unusual stones began to interfere with plowing. Some of the fragments were even used for practical purposes, such as being placed into harrows to aid in soil cultivation due to their heavy weight. The total mass of the Tsarev meteorite is estimated at approximately 1.5 tons, and it is classified as a stone meteorite. To better understand the exhibition, it is helpful to define the terminology used in meteoritics. Each meteorite receives a proper name, typically based on a geographic location, most often the nearest settlement. This practice is necessary to distinguish the numerous meteorites found across the globe. All discovered meteorites are registered with the International Meteoritical Society, which includes a nomenclature committee. A brief description of each meteorite is submitted to the committee, which officially approves the name and confirms its status. Meteorites are classified as either falls or finds. A fall refers to a meteorite whose descent was observed, either visually or audibly, and which was recovered shortly thereafter, often on the same day. These are especially valuable, as they can be dated precisely in terms of both time and location. In contrast, a find refers to a meteorite discovered accidentally, often long after its fall, with only the year of recovery recorded. Meteorites are further classified by composition into three main types. Iron meteorites, such as Sikhote-Alin, consist almost entirely of native nickel-iron alloy, with nickel content typically exceeding 5%, which is a distinguishing feature of meteoritic metal. Stone meteorites, such as Tsarev, are composed of silicate material with compositions resembling basalt, a common terrestrial rock. However, what differentiates them from ordinary terrestrial rocks is the presence of native metal inclusions, specifically nickel iron, which gradually oxidize in Earth's atmosphere, giving these meteorites a rusty brown coloration over time. Stony-iron meteorites contain approximately equal parts silicate material and metal, and are referred to as stony irons. The frequency of occurrence of these types varies significantly. Among witnessed falls, stone meteorites constitute approximately 96%, iron meteorites about 3.5%, and stony irons around 1.5%. However, among meteorite finds, the statistics shift, as iron meteorites, being more resistant to weathering, are better preserved and thus overrepresented in the historical record, making up around 40% of older finds. In contrast, stone meteorites are more fragile and degrade more quickly, whereas stony irons remain relatively rare, comprising only 3 to 5% of discovered specimens. Before you are some of the most visually impressive meteorites in our collection. These meteorites were collected immediately after their fall and therefore represent the typical appearance of falls. Their surfaces are coated with a fusion crust, a thin melted layer formed during atmospheric entry, generally no thicker than 1 millimeter. Prominently displayed are specimens such as the Karakol meteorite, a well-known example often featured in encyclopedias. It has a remarkably symmetrical, aerodynamic conical shape. When a meteorite travels through Earth's atmosphere, the flight lasts only about 5 seconds, during which it loses between 80% and 99% of its mass due to ablation. Many meteorites fragment mid-air, a characteristic behavior that results in what is termed a meteorite shower, where hundreds of fragments may reach the ground. However, in rare cases where meteorites do not fragment and maintain a fixed orientation during descent, i.e. without tumbling, the ablation process, melting followed by material being blown off, can result in an ideal conical form, as observed in the Karakol and Nikolaevka meteorites. Such well-formed specimens are rare in collections. Before you also lies the Repeev Khutor iron meteorite, which resembles the head of a projectile or a missile. There are two very common misconceptions among the general public regarding meteorite falls. First, when a person sees a bright bolide, it often leaves an unforgettable impression. Statistically, a person may witness 1 or 2 such bright fireballs in their lifetime. The natural reaction is to assume the object fell nearby, perhaps 500 to 700 meters ahead, prompting witnesses to rush toward the perceived impact site. Often, they dig in the soil and bring us a rock, claiming it to be a meteorite, but almost invariably, what they bring is not a meteorite. This illusion arises because the luminous phenomenon is visible from great distances, far greater than the physical object itself. In reality, meteorites typically fall 20 to 30 kilometers away from the observer, making it virtually impossible to locate the meteorite without precise instrumentation. The actual meteorite may be small, roughly the size of a fist, making it extremely difficult to detect in the field. The second misconception concerns the appearance of meteorites. People often imagine that a body entering the atmosphere must emerge looking like pumice or slag, with a porous or bubbly texture. In reality, this does not happen, and here's why. Meteorites enter the atmosphere at cosmic velocities, averaging around 15 kilometers per second. The fusion crust that forms on the surface melts and is immediately blown away by the slipstream. The smoky trail that follows large meteorites or bolides is composed of vaporized meteoritic material, which then condenses into microscopic spherules and gradually settles to the ground. Crucially, the body does not heat up internally. The outer layers ablate rapidly, but the core remains unaffected. Atmospheric drag slows the body significantly, and smaller meteoroids, such as those that produce visible fireballs, come to near aerodynamic halt at altitudes of 5 to 10 kilometers. After this point, the body falls freely under gravity, much like a dropped object, and has time to cool during the final 10 to 15 kilometers of descent. Thus, if a witness retrieves a freshly fallen meteorite, even within minutes, it is typically not hot. The internal temperature does not exceed ambient, as heat from the outer layers penetrates only about 5 millimeters inward, reaching up to 200 degrees Celsius. This is clearly visible in iron meteorite cross-sections. Metal conducts heat efficiently and rapidly undergoes recrystallization. The interior remains at approximately 0 degrees Celsius, akin to temperatures in Earth's orbit. Therefore, meteorites undergo very little alteration during atmospheric entry. Had they melted completely, they would no longer be scientifically useful. Meteorites are unique relics of the early solar system, dating back 4.5 billion years, and they have remained unaltered since their formation. These small celestial bodies avoided incorporation into planets and have persisted across cosmic history. Meteorites continue to fall on Earth as these remnants approach from space. Many visitors to our museum ask how to distinguish meteorites from ordinary rocks. Understandably, as the idea of finding a meteorite is fascinating, albeit exceedingly rare. Discovery is almost always accidental, and only a few fortunate individuals succeed. Unlike other scientists, e.g., geologists or biologists, who can actively collect specimens in the field, meteoriticists depend entirely on chance discoveries made by members of the public. Only in areas of known meteorite falls can targeted searches be conducted. So how can one tell a meteorite apart? In practice, only experts, most often geologists familiar with terrestrial rocks, can reliably differentiate meteorites. However, there are several practical indicators accessible to the general public. Meteorites are denser than most Earth rocks. If a person witnesses a rock fall and picks up a heavy, unusual-looking stone, they may correctly suspect it is a meteorite. If someone stumbles upon a rusty, unusually heavy brownish rock while hiking or mushroom picking, it could be a meteorite. Most meteorites contain native metal, typically nickel iron, which oxidizes over time, giving the rock a characteristic brown coloration when buried in the ground. Even stone meteorites are denser than average terrestrial rocks. While typical rocks have a density of 2.8 to 3.0 grams per cc, stone meteorites may reach 3.5 to 3.7 grams per cc. Iron meteorites, on the other hand, can have a density of approximately 8 grams per cc, similar to industrial metals. So when someone picks up such a heavy, rusty stone, its unusual weight is one of the strongest clues that it may indeed be a meteorite. In meteorites, when a fresh fracture is observed, there is typically no layering or porosity, only very densely packed material. Importantly, organic remains, such as fossils or shell fragments commonly found in limestone, are never present in meteorites. These are among the key distinguishing features. If the metal is rusty, distinguishing meteoritic iron from industrial metal becomes possible only through laboratory analysis, as the physical properties, such as density, are quite similar. However, meteoritic metal is chemically distinct due to the presence of several percent of nickel, which is absent in most terrestrial iron. It is even likely that iron meteorites played a role in the early development of human technology. Ancient humans, encountering such an unusual metallic material, foreign to common rocks, may have fashioned tools or artifacts from it. After all, smelting iron from ore is a technologically complex process that required significant societal advancement. Thus, early encounters with meteorites may have stimulated technological innovation. The external appearance of meteorites is also somewhat characteristic, although not universally so. For instance, the Karakol meteorite shows a distinct ring of indentations, or regoliths, shallow grooves formed by vortices in atmospheric flow during descent. These indentations provide a textural signature of atmospheric ablation. However, some meteorites exhibit smooth surfaces, which suggests they rotated steadily along a fixed axis during atmospheric entry. In such cases, regoliths do not form. Regoliths are especially prominent on Sikhote-Alin specimens, where they resemble the imprints of giant fingers in clay. It has been observed that the size of these regoliths correlates with the size of the meteorite itself. Our collection includes a unique fragment that broke off a much larger parent body. Its upper surface exhibits large regoliths, with depressions the size of a human palm, while the lower surface features finer textures. This phenomenon was confirmed through special measurements conducted on numerous Sikhote-Alin meteorites. In our display cases, smaller meteorites are arranged in chronological and typological order. One case is dedicated to historical meteorites, arranged such that the right section contains recently fallen meteorites, collected shortly after impact, while the left section contains finds, meteorites discovered years or decades after falling. This organization allows us to observe how meteorites change over time when exposed to Earth's surface. Our atmosphere is highly corrosive to meteoritic metal, which inevitably oxidizes, even under museum conditions. This presents an ongoing conservation challenge. Some of the oldest meteorites may have completely rusted away, leaving no trace. A typical example of a fresh fall is the Karakol meteorite. It has a thin, matte black fusion crust, formed as its surface melted during atmospheric entry. Inside, it reveals a light gray, fine-grained, dense rock. Most meteorites of this type, stone meteorites, look very similar. Now, let us turn to historical finds. Here before you are two small fragments of the famous Pallas Iron, also known as the Krasnoyarsk meteorite, the foundation of our collection. This mass was found in Siberia in 1749, and it drew attention due to its high metal content. The mass was transported from the taiga and preserved in a local estate. When academician Peter Simon Pallas traveled through Siberia, the unusual mass was presented to him. Recognizing its uniqueness, he brought it back to St. Petersburg. This is the only meteorite in history named after a person, Pallas, and today Pallasites are recognized worldwide as a distinct class of Stony-iron meteorites, named after this very specimen. It is a landmark discovery, and the original Pallas Iron occupies a major display case in the Fersman Mineralogical Museum. The mass was initially housed in the Kunstkamera, then later sawed into two slabs, which now occupy an entire exhibition cabinet. What you see here are small fragments, including a cut and polished surface, and a natural broken edge. This type of meteorite displays extremely heterogeneous composition. Pallasites are stony iron meteorites, composed of silicate crystals, mainly olivine, visible here as dark inclusions, and metallic matrix, which appears bright and reflective. In some broken samples, the metal may appear porous, like a sponge, but in fact, the rock is densely packed. This appearance results from the brittle olivine crystals being dislodged under mechanical stress. This specimen forms the cornerstone of our collection. This section of the exhibition presents historical meteorite falls that occurred at the turn of the 18th and 19th centuries. One of the most famous is the Laguel meteorite, which fell in France in 1803. An estimated 2,000 to 3,000 stones fell, practically striking eyewitnesses on the head. Another notable fall is the Weston meteorite, which fell in America in 1807 and was also widely observed. Earlier still was the fall of the Kharkov Zhyhilivka meteorite in 1787, which was also witnessed by many observers in Ukraine. These three significant events, together with the discovery of the Pallas Iron meteorite, fundamentally changed public and scientific perception. In the Middle Ages, even scientific authorities were skeptical of eyewitness reports, believing that stones could not fall from the sky. Such accounts were dismissed as fabrications or misunderstandings. However, the discovery of the Pallas Iron and the highly visible falls of Laguel, Weston, and Kharkov dramatically shifted this paradigm. It was no longer possible to deny that meteoritic stones were falling from space. These events led to the first chemical analyses of meteorites, which were conducted to understand the composition of these extraordinary celestial bodies. Thus, from the late 18th century onward, meteorites began to be systematically collected and studied as extraterrestrial visitors to Earth. Another historically interesting case is the Borodino meteorite, which fell on the eve of the Battle of Borodino in 1812 during the Napoleonic Wars. In 2012, the bicentenary of the battle was commemorated. The meteorite fell into the encampment of Russian troops, who were assembled on the night before the battle. It was discovered by a sentry and handed over to his commanding officer. Fearing that it might be seen as an ill omen, the commander withheld the information, and the meteorite remained in his estate for nearly a century before being acquired by a private collector. Among more recent major meteorite falls in Russia, one of the most remarkable is the Sterlitamak meteorite, which fell on May 17, 1990. Photographs in the exhibit show the crater created upon impact, a 10-meter-wide depression, into which the iron meteorite penetrated to a depth of 10 meters. Fragments of the meteorite were ejected from the crater during the impact and can also be seen in the exhibit. A bright fireball was observed over the city of Ufa, and the meteorite landed in a field just 2 kilometers from a nearby village. The shockwave shattered windows in the village, prompting residents to believe that a war had begun. Despite its scientific significance, the meteorite was never recovered because the crater filled with water within days. The meteorite had pierced an aquifer, forming a small lake approximately 50 meters wide, now used for swimming. Retrieving the meteorite would require expensive drainage and excavation, involving 2 separate shafts, and no funding has been allocated for such an endeavor. Also present in this display case is one of the smaller meteorite specimens. The Sikhote-Alin meteorite remains the largest meteorite whose fall was directly observed. However, in terms of total mass, there are meteorites that exceed the Sikhote-Alin meteorite. The largest single intact meteorite by mass is the Hoba meteorite in Africa, which weighs 60 tons and remains at its original site of impact. Another unique specimen in the collection is the Kutais meteorite, which is among the smallest by weight, just 23 grams. This fall occurred on the morning of November 28, 1977, in the village of Kutais, Krasnodar region. 2 women walking to work at 8 a.m. stopped to talk, and a stone whistled past, landing just meters from them. They picked it up and discovered that it was a cone-shaped meteorite. The specimen was later given to a local school astronomy teacher, through whom it entered the museum's collection. There are also instances of micrometeorite showers, consisting of stones as small as half a centimeter. These are extremely rare and only preserved when collected immediately after the fall. One of the oldest meteorites still in existence is the Ensisheim meteorite, which fell in France in 1492. Its survival is extraordinary, as many historical meteorites have since been lost. The Ensisheim meteorite was witnessed by a large number of people, and its cultural impact was profound. It was chained to a church to prevent it from returning to the sky, reflecting the medieval worldview of the time. It features prominently in church chronicles, including numerous drawings and eyewitness descriptions. One final funny case. The Peekskill meteorite fell in the United States and famously struck a parked car, piercing the trunk of the vehicle. The owner gained brief celebrity status, and the insurance company paid out compensation. The meteorite weighed 12 kilograms. This meteorite was later identified as one of only 5 meteorites in history to be captured on video during flight until 2012. It happened during a football game, and the meteor was filmed from multiple locations, providing extraordinary documentation of the fall. On the left side of the display case, the transformation of meteorites over time is shown. This is a vital aspect to understand, as the majority of meteorites are discovered many years after their fall, and are therefore considered finds. Such specimens are presented here. In front of you is a well-preserved example, the Ivanovka meteorite. It was discovered in 1983 by schoolchildren in Tatarstan, lying in a field. Stone meteorites are often found in plowed fields, where no other rocks are typically present. During systematic tilling, meteorites appear to be pushed to the surface. A year later, the same group found a second specimen of the same meteorite. To the right is a poorly preserved find. This specimen is so altered that it closely resembles an ordinary terrestrial rock and can only be distinguished by a specialist. This is the famous Berdyansk meteorite, discovered during an archaeological excavation. Archaeologists uncovered a stone pyramid in a burial mound, where only one of the stones turned out to be a meteorite. Though dark and worn, it remains a meteorite. Another prominent fall was the Nikolaevka meteorite, a rather unfortunate case for science. A bright fireball was observed over the Omsk region in 1929. Later, farmers mowing a meadow reported hitting stones with their scythes. They attempted to investigate them primitively, often breaking them. By the time a scientific expedition arrived, most of the meteorites were gone. After an 8-year search, only one specimen was recovered, from a farmer's house, where it had been used as a weight for a barrel of sauerkraut. It had significantly rusted by then. Here is another altered meteorite, Bikardik, from the Turkmenistan desert. Its surface is encrusted with iron oxide nodules. These secondary minerals result from interactions with the Earth's atmosphere, gradually changing the surface and internal composition. In many stony meteorites, like this one from the desert, the polished surface reveals a significant amount of metal. The shiny patches are metallic. Near the surface, this metal oxidizes and vanishes. One of the first Antarctic finds, the Lazarev meteorite 1961, is shown here. It was named after the Soviet Lazarev station and is a metallic meteorite. Also shown is the Clipperton meteorite, recovered in 1986 from the Pacific Ocean floor. Soviet marine geologists, while conducting deep-sea trawling operations at depths of approximately 5 kilometers, retrieved rocks from the ocean floor, among which was discovered a meteorite. Given that the vast surface area of the ocean accounts for the majority of meteoritic falls, it is surprising that, until recently, no systematic attempts had been made to search for meteorites in marine environments. This represents a remarkable serendipitous discovery. Such cases continue to occur today. Sampling the seafloor has enabled the recovery of meteorites from the ocean bed. Despite extensive surface oxidation, iron transforming into oxides, the meteorite's internal structure remained relatively well preserved. To date, approximately 2,000 meteorites have been found across all continents. However, over the past 3 decades, two major natural meteorite collectors have been identified: the Antarctic ice sheet and the deserts of Africa. These environments have yielded thousands of meteorites, many of which have been preserved for centuries or even millennia. In Antarctica, meteorites become embedded in glacial ice, effectively shielding them from weathering. In Africa, meteorites are typically discovered on high-altitude plateaus where continuous winds scour the surface. If the host rock is light in color and relatively soft, such as limestone, the dark meteorites stand out in stark contrast, making them more visible. This display case presents such finds from desert environments. Thanks to these two natural collectors, by the year 2012, over 23,000 meteorites had been identified on Earth. This mass recovery is of paramount importance to the field of meteoritics. Among such a large number of samples, rare and previously unknown types have been identified, including lunar meteorites and members of the so-called SNC group, a class of meteorites now believed to originate from Mars. The next display showcases one of the most abundant types of meteorites, stony meteorites. While stony meteorites account for approximately 96% of all observed meteorite falls, they are classified into two major subgroups. The meteorites exhibited here belong to the group known as chondrites. The term chondrite is derived from the Greek word chondros, meaning grain. As shown in the sample, the meteorite contains rounded silicate inclusions known as chondrules, from the same Greek root. These chondrules can vary in size, from a few millimeters to over a centimeter, but typically measure fractions of a millimeter in diameter. Meteorites display a wide range of mechanical properties, from very solid and compact varieties to extremely fragile examples, such as the Ivanovka meteorite. In the provided thin section, one can observe cavities where chondrules have dislodged, clearly illustrating their size and abundance. A particularly striking example is the Manich meteorite, discovered in Russia. Its cross-section reveals numerous clearly defined round silicate chondrules, highlighting the meteorite's classic chondritic texture. Chondrules are regarded as primary condensates from the protoplanetary nebula, the early gas and dust cloud that gave rise to the solar system. These were among the first solid particles to form, well before the accretion of planets. After condensation, these particles were subsequently consolidated to form chondritic meteorites, representing the pristine, unaltered material of the solar system, estimated to be 4.5 billion years old. In this display case, you can see a complete classification of ordinary chondrites. It is apparent that there are notable variations among them, as illustrated by the specimens in this row. In these samples, a high metallic content is clearly visible in the cut surfaces. All reflective areas represent native nickel-iron alloy. In the next group, the metallic content is somewhat lower, and in the subsequent one, lower still. The rearmost row features chondrites in which the chondrules, spherical silicate inclusions, are very clearly and distinctly defined. This corresponds to the so-called petrologic type 3. In contrast, the lower rows display meteorites in which the chondrules are barely visible or not distinguishable at all, reflecting the diverse structural variations within this type of meteorite. On the left side of the case, carbonaceous chondrites are displayed, including the famous Allende meteorite, which fell in Mexico with a total recovered mass of 2 tons. The environmental conditions there were highly favorable for recovery, and the meteorite was collected rapidly. This led to a surge in scientific interest, as there was an ample supply of material for research. These meteorites are commonly referred to as carbonaceous chondrites, though the term is somewhat misleading. A more accurate designation would be carbon-rich chondrites, but the original terminology has become well established. They are often coal-black in appearance and are notable for containing complex organic compounds with molecular masses of up to approximately 350 atomic mass units. These molecules are chemically diverse and structurally intricate. Studying such meteorites is methodologically challenging due to their scarcity. The atmospheric entry process often destroys much of the mass, and what remains is distributed in small quantities among collections worldwide. Furthermore, extracting and analyzing their organic content requires sacrificing a significant portion of the sample, an often prohibitive cost. Carbonaceous chondrites can contain up to 2.5 to 3.5% carbon by mass. Remarkably, some also retain structurally bound water within silicate minerals, either as hydroxyl groups, O, or as hydrogen oxide molecules. Among the most famous are Migay, Russia, the namesake of the CM subgroup of carbonaceous chondrites. Murchison, Australia, noted for its diverse organic composition. The highest concentrations of both organic matter and water have been identified in the Orgel meteorite, which fell in France and belongs to a different subgroup of carbonaceous chondrites, CO type. If one were to fully extract the water from such meteorites, the water content could amount to nearly 28%, which is an exceptionally high concentration. This water is bound within the structure of so-called phyllosilicates, layered silicates, present in the meteorite material. Carbonaceous chondrites contain almost no metallic components, which makes them relatively fragile and structurally weak. Importantly, the organic compounds within these meteorites are abiogenic, formed without biological processes. No definitive signs of extraterrestrial life have been identified. However, amino acids, fundamental building blocks of life, have been detected, raising intriguing questions about prebiotic chemistry. If such carbonaceous material had arrived in large quantities during Earth's formation, it would have constituted an ideal substrate for the origin of life, providing complex organic molecules and water, needing only the right environmental conditions to catalyze life's emergence. Nonetheless, the origin of life remains one of science's most complex and unresolved challenges, making these meteorites crucial to astrobiological research. Carbonaceous chondrites are also notable for their chemical composition, which closely mirrors the elemental abundances observed in the solar photosphere, excluding the volatile elements, e.g. hydrogen, helium, nitrogen, carbon, sulfur. The 4 most abundant elements are silicon C, oxygen O, iron Fe, magnesium Mg. These 4 major rock-forming elements dominate the composition of planetary bodies. If one considers the abundance of approximately 70 non-volatile elements, their relative concentrations in carbonaceous chondrites are in near perfect agreement with the cosmic element distribution, a pattern sometimes referred to as the cosmochemical elemental abundance. The close match between chondrites and the Sun's non-volatile element spectrum underscores their primordial status in the solar system and establishes them as reference standards for planetary geochemistry. There also exist geological hypotheses concerning the internal evolution of planetary bodies. If we take ordinary chondrites, which, as can be observed, contain a significant amount of metal in some cases, it is conceivable that within the interior of a differentiated planetary body, such material could undergo partial melting. Under the influence of gravity, the metallic component could migrate toward the planet's core, while the outer shell or crust would consist of a different class of stony meteorites known as chondrites. The intermediate layer between the core and the crust would then be represented by a mixture of metal and silicates, corresponding to what we classify as Stony-iron meteorites. This model presents one line of reasoning, though it remains an open question subject to further scientific inquiry. Did such differentiation indeed take place? Therefore, chondrites are often referred to as indifferentiated material of the solar system, primordial matter. In contrast, other meteorite types, iron, stony iron, and achondritic meteorites, are considered differentiated material of the solar system. Notably, there are no direct terrestrial analogues to chondritic material. Such rocks are unknown on Earth. Chondrites represent a unique lithology of the solar system. Their formation process remains poorly understood and poses a significant enigma in planetary science. Moving forward, we encounter examples of differentiated meteorites. Before you is a display case of iron meteorites. The right-hand section features specimens from the renowned Sikhote-Alin meteorite fall, one of the largest observed meteorite events on our territory. These samples illustrate the external morphology of iron meteorites, while the left-hand side showcases their internal metallic structure, which is itself both unique and enigmatic. Let us first consider the external appearance. Here we see various fragments of the Sikhote-Alin meteorite, both large and small. One specimen displays multiple fractures, an example deliberately included to demonstrate how fragmentation occurs during atmospheric entry. As the meteorite descends, it experiences uniaxial compression, as though being squeezed by a press, because it encounters immense air resistance at hypersonic velocities, typically several kilometers per second. When the dynamic pressure exceeds the structural integrity of the meteorite, cracks form and propagate, eventually causing the body to break into individual fragments. Each fragment then continues its descent, melting at the surface due to frictional heating. You can observe strongly melted, aerodynamically smooth specimens resembling pebbles. These are fragments that separated relatively early in the descent. Displayed in this case are fragments of a meteorite that separated from the main body at the very last moment before impact. These pieces exhibit minimal melting and have been only slightly affected by atmospheric entry. Their surfaces display very fine regmaglyptic relief, through which internal structural features of the meteorite become visible. In some instances, monocrystals of iron protrude, revealing peculiar shapes that often evoke associative imagery. While these are not the smallest fragments recovered, micrometeorites weighing mere milligrams have been found in the distal parts of the strewn field ellipse. These samples represent visually striking forms, including a conical piece with visible solidified melt splashes, and others shaped like a bullet with a melt flange, or even resembling a knight chess piece or seahorse. All of these specimens are meteorite fragments covered with fusion crusts, formed during atmospheric passage as a result of fragmentation in flight. However, in the right section of the case are twisted and deformed pieces, similar in appearance to shrapnel fragments, which were generated by the impact event upon collision with the Earth's surface. Massive meteorite bodies, weighing over a ton, failed to decelerate fully and impacted solid bedrock at high velocity. This caused both the meteorite and the surrounding target rock to shatter. These shrapnel-like fragments show clear mechanical deformation, including striations indicative of high-stress fragmentation. Iron meteorites, being structurally stronger than stony meteorites, exhibit such features prominently. To the left side of the display, the internal metallic structure of iron meteorites is presented. Notably, 2 samples of the Sikhote-Alin meteorite are featured, known for their coarse structure, which accounts for their tendency to fragment. Cracks propagate more readily along grain boundaries than through the crystals themselves, as the crystals possess greater mechanical strength. Consequently, small meteorite fragments often adopt unique and unusual shapes. The coarse crystalline pattern seen in many iron meteorites is known as the Widmanstätten structure, or octahedrite structure. This name reflects the crystallographic orientation of the iron-nickel plates, or lamellae, which are aligned with the faces of an octahedron. When cut, these lamellae reveal characteristic triangular or trapezoidal patterns at 60 degrees angles. This regular geometric pattern forms due to the exsolution of a solid solution during extremely slow cooling of an iron-nickel alloy. As the alloy cools from its melting point, it separates into 2 phases. Kamacite, a low nickel iron phase containing about 6 to 7% nickel, visible as broad metallic lamellae. The second phase is represented by taenite, a high nickel phase that contains between 20% and 60% nickel. In certain areas of the meteorite, if one catches the glint of a lamp, the visual effect is reversed. The broader lamellae appear dark, while along their borders one can observe extremely thin, brilliantly white metallic bands. These narrow, bright ribbons correspond precisely to the taenite phase. This phase is especially distinct under microscopic examination, where its high reflectivity and fine scale contrast markedly with the surrounding kamacite. The scale of the Widmanstätten structure depends on 2 independent parameters: the overall nickel content and the rate of cooling. For example, in the Sikhote-Alin meteorite, which contains about 6.5% nickel, the structure is very coarse and referred to as a very coarse octahedrite. This particular specimen, in fact, does not exhibit a true octahedrite structure at all. What one observes instead are patches of varying degrees of rust, which correspond to individual monocrystals of kamacite. Due to their differing crystallographic orientations in space, these kamacite grains oxidize at different rates, leading to the irregular appearance. Notably, this oxidation process occurs even under museum conditions. Meteoritic iron inevitably and gradually transforms into oxides over time. In the Sikhote-Alin meteorite, the bulk nickel content is approximately 6.5%, resulting in a very coarse octahedrite structure. In contrast, a meteorite with a moderate scale structure typically contains about 8% nickel. In fine octahedrites, the nickel content rises to around 10%, while in very fine octahedrites, it can reach approximately 12%. When nickel content exceeds 14%, as in the Chinga meteorite, the Widmanstätten pattern no longer develops. Instead, the structure becomes finely crystalline, barely discernible even under magnification. To reveal this structure, meteorite surfaces must be polished to a mirror finish and then etched, after which the microscopic grain boundaries of the metal become visible. Such fine-grained structures resemble those in industrial steels. But the large grain sizes in many meteorites cannot be replicated in laboratory or industrial conditions. For the crystals to reach millimeter or centimeter scale, as seen in meteorites like Sikhote-Alin, cooling rates must be as slow as 1 degree Celsius per million years, a condition impossible to reproduce in artificial environments or even deep within terrestrial planetary bodies. This remains a natural enigma, suggesting that these structures formed under cosmochemically unique conditions. Among iron meteorites, one rare and fascinating type includes monocrystals of iron. It is exemplified by the Boguslavka meteorite. Here is a small fragment of it. This portion of the meteorite was sawn off for study. The meteorite itself is part of the permanent exhibition at the Fersman Mineralogical Museum. It stands approximately 1 meter tall and weighs about 200 kilograms. It is an iron monocrystal, a remarkably rare and beautiful specimen. The question of where such massive single crystals of iron could have formed remains unresolved. There exists a particular class of meteorites characterized by large iron crystals ranging in size from centimeters to decimeters, and in the case of our exhibition, up to a full meter, as exemplified by the Boguslavka meteorite. This meteorite's fall was witnessed and even captured in a 1916 watercolor painting by an eyewitness, documenting the Boguslavka meteorite's descent over the Russian Far East. These are truly extraordinary and enigmatic meteorites. On cut surfaces, other minerals can be identified beyond kamacite and taenite. These include Schreibersite iron 1 phosphide, a long needle-like iron phosphide which in the Sikhote-Alin meteorite resembles intricate hieroglyphic patterns. One can observe rounded inclusions within the specimen. These are iron sulfide, specifically troilite. Troilite is a typical accessory mineral, or minor phase, that occurs in almost all types of meteorites. In addition to the major metallic phases, there exist pelazite fields, which represent a finer and more evolved stage of metal crystallization. These regions often contain residual nickel, and the bulk nickel content is typically higher in these local areas, which leads to the formation of finer structural patterns. These appear as dark interstitial regions between kamacite lamellae, often taking the shape of triangles or trapezoids. Essentially, they are the same type of exsolution structure as the Widmanstätten pattern, but formed on a different scale. Various configurations may occur, ranging from the highly regular geometry of a classic Widmanstätten structure to granular or irregular morphologies, depending on cooling history and composition. Within such troilite nodules, as they are commonly termed, one can also frequently find rim structures. Additionally, accessory phases like graphite and cohenite iron carbide, may be observed, especially around troilite nodules. This constitutes the typical mineral assemblage found in many iron meteorites. In general, the mineralogical diversity of meteorites is somewhat limited when compared to terrestrial rocks. At one stage of meteoritic research, for comparison, while approximately 2,000 minerals had been documented in Earth's crust, only about 700 minerals had been identified in meteorites. Nonetheless, several minerals were first discovered in meteorites. These are typically present in trace amounts, and large crystals are rarely encountered. When present, they can be observed either in thin sections or as inclusions identified by specialized techniques. These accessory mineral phases often provide critical insights into the conditions under which the meteoritic rock formed. In many cases, such microscopic features are initially identified in meteorites and later found on Earth, or vice versa. Thus, over time, the mineralogical diversity observed in extraterrestrial and terrestrial materials tends to converge. The next display case is also dedicated to differentiated types of meteorites. The specimens on the right are classified as Stony-iron meteorites, comprising approximately equal volumes of metal and silicate phases. The rightmost portion of the case displays pallasites, a group named after the historic Pallas Iron meteorite. Pallasites are mineralogically simple. The silicate phase is predominantly olivine, and iron-magnesium silicate. Other minerals are present in minor quantities and are considered accessory. The adjacent row features another type of stony iron meteorite, characterized by a different distribution of metallic phases. The silicate component here is more complex, consisting of two primary minerals, pyroxene, an iron-magnesium silicate, and plagioclase, a calcium-aluminum silicate, commonly referred to as feldspar. This group of stony iron meteorites is classified as mesosideриtes. Pallasites, when well prepared and polished, reveal visually stunning internal structures. They may contain large, gem-quality olivine crystals that, in thin section, can be transparent. The majority of pallasites are classified as fines, with their exact fall dates unknown. However, one documented pallasite fall has occurred on Russian territory, the Omolan meteorite, which fell in Chukotka. Omolan is notable for its exceptionally large, nearly gem-quality olivine crystals. While aesthetically appealing, these should not be used for jewelry due to the scientific value and rarity of the material. Such use would be considered destructive. Upon impact, Omolan created a small crater on a rocky slope with a thin soil layer. The shock of impact caused the olivine crystals to fracture, making them prone to disintegration. This illustrates a common phenomenon. If a meteorite does not completely decelerate before impact, the brittle olivine phase may crack, resulting in irreversible damage. On the left side of the display case are stony meteorites. Earlier, we examined chondrites, unique lithologies with no known terrestrial analogues. In contrast, the current section features chondrites. The prefix A denotes the absence of chondrules, which characterizes this group. Achondritic meteorites can often be compared to planetary materials, as they resemble terrestrial basalts in both mineralogy and structure. Basalts are widespread on Earth, forming the oceanic crust and vast igneous provinces. Similarly, basalts have been identified on other rocky planets visited by spacecraft, namely the Moon, Mars, Venus, and Mercury. The most common achondritic meteorites belong to the group known as basaltic achondrites. These meteorites are composed primarily of two major rock-forming minerals. An example is the Chervony-Cut meteorite. Its mineral composition is visible to the naked eye. The white mineral is plagioclase feldspar, a calcium-aluminum silicate, and the black mineral is pyroxene, an iron-magnesium silicate. This specific meteorite is notable for being unbrecciated, which is relatively uncommon, as most basaltic achondrites occur in the form of breccias, rocks composed of angular fragments of earlier rocks. These breccias can be classified further into monomict breccias, composed of fragments of the same type, and polymic breccias, which contain fragments of varying types. For example, the Capoeira meteorite is a polymic breccia, representative of the howardite class, while Vetluga is a monomict howardite, comprising fragments of a single lithology bound together by fine-grained clastic material. Within the achondrite group, there are rarer and even exotic types. Some, such as the Peña Blanca Spring and Norton County meteorites, are almost white to light gray and composed almost entirely of large crystals of the magnesium silicate enstatite. In pyroxene minerals, iron and magnesium are typically interchangeable in the crystal lattice. Most meteorites exhibit intermediate iron to magnesium ratios. However, the enstatite chondrites, obrites, are distinguished by their extremely low iron content, less than 1%, and correspondingly high magnesium content in their pyroxenes, resulting in a near-pure enstatite composition. The formation of these meteorites occurred under conditions of extremely low oxygen fugacity, strongly reducing environments. In such conditions, elements like manganese, titanium, chromium, and calcium, which under normal conditions, both terrestrial and meteoritic, tend to bond with oxygen and enter silicate structures, instead form their own sulfide minerals. These sulfides, once on Earth, are highly susceptible to weathering. For instance, oldamite, a calcium and sometimes magnesium sulfide, is water-soluble. This makes careful handling and conservation critical. Improper methods, such as wet cutting, can irreversibly damage the meteoritic material. Special precautions must be taken to avoid dissolving sensitive mineral phases during processing. These obrites contain little to no metallic iron and are very fragile. Even their fusion crusts, such as that of the Pezunoi meteorite, are semi-transparent and range from dark to light gray, but never black, as is typical for more robust meteorites. Another exotic group among achondrites is represented by euryalites, such as the Novo-Urei meteorite from Russia, which fell in 1886. Chemists studying the meteorite in the late 19th century discovered nanometer-scale diamonds of extraterrestrial origin within its matrix. Though too small to be seen with the unaided eye, these microdiamonds are abundant and pose challenges during cutting and polishing. Carbon in these meteorites may also be present in graphitic form, the softest mineral counterpart to diamond. The discovery of diamonds in Novo-Urei led to the naming of the entire class of ureilites after this meteorite. These meteorites are characteristically black and contain complex carbonaceous phases. Even more exotic types of achondrites include the so-called lunar meteorites, such as the two specimens recovered from Antarctica. These meteorites represent different regions of the Moon's surface. Another rare group includes the SNC meteorites, a proposed set of meteorites originating from Mars. The prevailing hypothesis is that these rocks were ejected from the Martian surface during meteorite impacts. Displayed here on a pedestal is a sample of lunar regolith, shown at 2x magnification. The specimen weighs approximately 6 grams and was collected by the LUNA-16 automatic probe in 1970, which landed in the Mare Fecunditatis, Sea of Fertility, on the Moon. This mission marked the first successful automated return of lunar material, delivering a total of 105 grams of soil. In total, the Luna 16, Luna 20, and Luna 24 missions returned 325 grams of lunar regolith. At Vernadsky Institute, the regolith is stored in a specialized room under a protective atmosphere of nitrogen and helium. The capsule on display here contains lunar soil sealed in a nitrogen atmosphere. It is essentially ultrafine dust from the Moon's surface, with an average particle size of about 70 microns. The sample remains unaltered and unseparated, preserved exactly as collected. In research settings, such material is analyzed under microscopes, allowing larger particles embedded in the regolith to be identified and studied. However, this display contains a fully unsegregated lunar soil sample. During full moon observations, distinct light and dark regions can be seen on the Moon's surface. The darker regions are traditionally called Maria or seas, while the lighter regions are referred to as highlands. Despite their name, the lunar Maria contain no water. These regions differ in composition. The highlands are rich in anorthite, a calcium-rich plagioclase feldspar, and the highland rocks are known as anorthosites. Therefore, these rocks are very light in color, as they reflect a significant amount of sunlight, making the corresponding areas on the Moon appear bright. In contrast, the mare regions are covered by a vast layer of basaltic lava. Basalt itself is of a dark, somber gray color, similar to the sample presented here. This sample represents finely fragmented basalt, originating from the lunar surface. The entire lunar surface is coated with this fine dust, known as the lunar regolith, which typically extends to a depth of 5 to 7 centimeters, but can reach up to 10 meters in the highlands and about 3 meters in the Maria. It is through this regolith that Apollo astronauts walked, while Soviet missions returned samples robotically. Soil collection was performed using a drilling device, and the return samples preserved the original stratification, reflecting layers of material from various impact events. The entire lunar surface is covered with craters, a result of meteoritic bombardment. Some of these craters reach up to 1,000 kilometers in diameter. On images, one can even see rays radiating from certain craters. These are ejecta thrown out during the impact event. In the highland regions, the upper layer of fragmented rock is estimated to be about 5 to 10 meters thick. In contrast, in the mare regions, the regolith layer is approximately 3 meters thick. The basaltic lunar maria represent a younger surface, which is reflected in the lower density of impact craters found there. Such is the nature of the lunar soil. Because the Moon lacks an atmosphere, any object, from a grain of sand to a massive asteroid, impacts the surface at full cosmic velocities, measured in kilometers per second. The resulting processes involve not only fragmentation of the impactor and target, but also melting and vaporization. This intense energy creates the regolith, a layer of pulverized rock that is a defining characteristic of airless planetary bodies. A critical fact is that, on average, 70% of lunar soil has undergone substantial thermal transformation, including melting and vitrification, resulting in glassy and slag-like phases. Only about 30% of the material consists of recognizable lunar rock fragments. This must be clearly understood when analyzing or collecting samples from airless planetary bodies. Lunar regolith differs markedly from meteorites, which generally preserve their primordial, unaltered state. The next display case is dedicated to natural terrestrial specimens, though not meteorites themselves, but rather rocks that have been profoundly altered by colossal impact events, much like those observed on the Moon. On the Moon, an object of any size striking the surface generates an explosion of tremendous force due to the absence of an atmosphere. On Earth, however, the atmosphere only ceases to significantly affect incoming bodies when their size reaches several tens of meters. At that scale, the Earth's atmosphere becomes effectively transparent, and such an object can strike the surface at full cosmic velocity. Upon impact, the projectile is shattered, melted, and vaporized, along with the target rocks at the impact site. These transformed rocks are presented in this exhibit. They are terrestrial rocks that have undergone physical and chemical alteration due to the passage of a shock wave. Such shock waves are supersonic and extremely powerful, altering the state of matter. These rocks are termed impactites from the English word impact and often resemble volcanic rocks. Historically, before impact geology was fully developed, geologists frequently misinterpreted circular surface structures and rocks of this nature as volcanic in origin. Yet, a meteoritic impact on Earth generates a shallow, flattened structure, not a volcanic cone. One prominent example, shown in the photograph, is the famous Beringer crater, also known as Meteor Crater, in Arizona, which is exceptionally well preserved. During such an impact, part of the target rock is melted, part is fragmented and ejected, forming a raised rim around the crater. The Beringer crater was formed by the impact of an iron meteorite known as Canyon Diablo. Fragments of this meteorite are still found both inside and around the crater. The crater itself is approximately 1,200 meters in diameter and about 200 meters deep. The estimated energy release was equivalent to 1.7 megatons of TNT, roughly equivalent to 7 Hiroshima-sized nuclear explosions. Such structures are referred to as astroblames, meaning star wounds, and while the Beringer crater may seem large, it is in fact modest in size by astroblame standards. Most are several kilometers or even tens of kilometers across. Their explosive energy corresponds to dozens or even hundreds of nuclear detonations occurring simultaneously. The rocks found within and around these craters provide key diagnostics for confirming the impact origin. These insights have been significantly advanced, unfortunately, through nuclear weapons testing, which produce similar rock transformations when conducted underground. Displayed here are fully melted rocks from impact craters. One sample resembles volcanic tuff, composed of rock fragments and glass shards. During an impact, massive volumes of molten material may be ejected from the crater, solidifying mid-flight into droplets. These natural glasses, formed by the rapid cooling of impact-melted terrestrial material, are known as tektites, from the Greek tektos, meaning melted. Tektites often resemble dumbbells, a shape resulting from unfused or incompletely separated molten droplets falling back to Earth in a semi-molten state. Their deformed shapes, flattened forms, tails, or curved edges testify to their plastic state at the moment of landing. Tektites correspond in composition to the target rock. Because the melt cools extremely rapidly following the sudden release of vast energy, these glasses are highly fragile. Thin sections of tektites range in color from brown to green and yellow. Tektites are found on every continent. In Indochina, the black specimens are called Indochinites. On the Philippines, spherical glasses known as Philippinites are common. This exhibit includes a giant Philippinite sphere. Very light-colored glasses, silica glasses, are found in deserts composed primarily of silicon oxide-rich sand, explaining their clarity. In Australia, unusual tektites known as australites resemble buttons. An inverted button specimen is shown here, with a blunt conical shape reminiscent of a re-entering meteorite. The separated flange is also preserved. One hypothesis suggests that such specimens were ejected beyond Earth's atmosphere during massive impact events and then re-entered, undergoing the same ablative melting as meteorites. This is supported by aerodynamic experiments, which reproduce their geometry with remarkable precision. Some of the most beautiful tektites are the bottle green moldavites from the Czech Republic, which exhibit both smooth and intricate morphologies. The extreme speed of formation is visible in striped black and white tektites. Their chemical components had no time to mix, resulting in sharp compositional banding. Interestingly, fields of tektite distribution and their source craters were often discovered independently. Today, around 200 confirmed impact craters are identified on Earth. The only geochemically confirmed link between tektites and a specific crater is that between the Czech moldavites and the Nördlinger Reis crater in Bavaria, Germany. This crater even houses the town of Nördlingen, where buildings are constructed from local impactites. Despite being over 200 kilometers from the site of the moldavite finds, it is believed that the Rise impact ejected molten material across this vast distance, an impressive measure of the blast's intensity. Another important crater is Zamenchin in Kazakhstan. The surrounding bedrock is composed of crystalline schists, and this is the only known terrestrial crater with associated tektites called ergizites. Though small in size, these glasses were found near the crater itself. Also displayed are massive glass bombs and striped glasses from this location. Under magnification, tiny nodules and droplets can be observed on the surface of the dumbbell-shaped tektites. These are a result of the coalescence of silicate droplets, a phenomenon that occurs during hyper-energetic events. The impact generates a silicate vapor cloud, from which microscopic droplets condense and fuse into larger, visible glass beads. In craters exceeding 5 kilometers in diameter, it becomes virtually impossible to detect remnants of the original meteorite, even by geochemical means in the glass. The energy of such impacts vaporizes, melts, and entirely obliterates the impactor's material. One of the largest known impact craters on Earth is the Chicxulub crater. It is estimated to have a diameter of approximately 180 kilometers and is located in the region encompassing the Gulf of Mexico and the Yucatan Peninsula. The crater exhibits a relatively regular semicircular shape. The formation of such a crater from the collision of a cosmic body with Earth's surface is essentially a planar phenomenon. The actual area affected by the initial impact is comparatively small, which means the number of immediate casualties may be limited. However, the consequences of such an event extend far beyond the impact zone. The collision can generate extremely powerful and destructive earthquakes, capable of affecting half a continent, as well as massive tsunamis with similarly far-reaching destructive potential. The most dangerous phenomenon associated with such impacts, however, is the release of fine particulate matter, akin to the effects observed during a nuclear explosion. This finely dispersed debris is carried throughout the atmosphere by air currents, leading to widespread atmospheric opacity and triggering a nuclear winter effect. Such global climatic disruption poses a severe threat to all living organisms, often resulting in mass extinctions. Indeed, such extinction events have occurred repeatedly throughout Earth's geological history. The Chicxulub crater, located in the Gulf of Mexico, is believed to have formed as a result of an asteroid impact by a body estimated to be 10 to 20 kilometers in diameter. The asteroid struck a shallow marine environment, and the resulting explosion caused widespread devastation, including the extinction of numerous species, most notably the dinosaurs, which were at that time both abundant and diverse. This near-complete extinction event illustrates how cosmic impacts can significantly influence the course of biological evolution on Earth. Geological evidence supporting this hypothesis includes the presence of impactites, rocks formed under the extreme conditions of impact events. In recorded human history, the only comparable phenomenon is the Tunguska event. Artistic depictions exist from an eyewitness who participated in the expedition to the epicenter. In 1908, a large object entered Earth's atmosphere and exploded in midair. One prevailing hypothesis is that the object was the icy nucleus of a small comet, approximately 100 meters in diameter, though more recent estimates suggest a size closer to 50 meters. The composition of the object is thought to have been primarily ice, typical of cometary bodies, which consist of frozen gases and water, with inclusions of silicate dust. The explosion occurred at an altitude of approximately 10 to 15 kilometers above Earth's surface. It was accompanied by a blinding flash so intense that trees were scorched at distances of tens and even hundreds of kilometers from the epicenter. Due to the dispersal of vaporized material in the upper atmosphere, a wide band of Earth, from Siberia to the Ural Mountains and as far as England, experienced continuous twilight with daylight-like conditions persisting such that newspapers could be read at dusk. At the epicenter, a massive forest blowdown occurred over an area roughly 40 kilometers in diameter. The tops of the felled trees were all oriented away from the explosion's center, a pattern clearly visible in photographs and sketches made during expeditions. The scene resembled a vast field of flattened grass. Such a pattern of destruction cannot be explained by any known natural or artificial cause other than a high-altitude explosion. Severe thermal radiation burns were observed on trees, many of which were left charred yet standing vertically within the epicenter, while all surrounding forest was leveled. Although the taiga has since regenerated, remnants of the damaged forest remain visible even today, though possibly not for much longer. The event itself was well documented, with aerial photography conducted in 1938. Nonetheless, the first major scientific expedition to the site, led by Leonid Kulik, reached the area only 2 decades after the explosion. This catastrophe, though slow in its influence, fundamentally altered human perception of planetary vulnerability. With the advancement of observational technology, the potential threat posed by near-Earth objects has come to be taken seriously. Entire groups of asteroids are now known to have orbits intersecting or approaching Earth's orbit, giving rise to the scientific and policy concept of asteroid hazard. It was the Tunguska event, initially thought to be caused by a meteorite, that awakened global awareness. However, given its composition, an icy body such as this could not have survived entry to reach the surface. The explosion occurred in the atmosphere, and no substantial fragments that could be physically recovered were found. This supports the interpretation that the event was caused by the atmospheric entry of a cometary nucleus. Thus, the Tunguska event served as a profound lesson for humanity, highlighting the necessity of preparedness for future encounters with cosmic visitors, some of which may occur within the coming decades.
We are currently at the Museum of Extraterrestrial Matter at the Vernadsky Institute of Geochemistry and Analytical Chemistry of the Russian Academy of Sciences. I'd like to highlight some interesting facts related to meteorite falls, discoveries, and specific specimens. Right in front of us is the Pervomaisky meteorite. It fell in the Vladimir region in the winter of 1933. The renowned Soviet scientist Leonid Kulik worked extensively on this case. He gathered local residents, who managed to collect a significant amount of material, 96 specimens in total. This might possibly be the only shot meteorite in existence. Hunters reportedly came across a black stone sticking out of the snow during winter, mistook it for a ferret, and fired at it. It's not impossible that the very specimen we see here is that one. It weighed around 9 kilograms and still bears the traces of buckshot. On the top shelf, 3 specimens are displayed that show what oriented meteorites look like. What does oriented mean? It means that during its descent through the atmosphere, the meteorite did not spin, but instead traveled steadily in one direction. In such cases, ablation occurs unevenly, producing distinct aerodynamic shapes. For example, the Karakol meteorite, considered the calling card of our museum and of the Academy of Sciences' Russian meteorite collection, is a classic example. It is a magnificent specimen weighing about 2 kilograms, which fell in Kazakhstan. Another oriented specimen with a rather unusual shape is the Repeev Khutor meteorite, from Volgograd Oblast, which also fell in 1933. Next is the well-known Chelyabinsk meteorite, which needs no introduction. A research team from Vernadsky Institute took part in the recovery expedition, arriving just 3 days after the fall and collecting numerous small fragments. These fragments are represented here in 2 forms, as ordinary chondrite and as impact melt. This display case contains a wide variety of material, but I'd like to highlight just a few more notable specimens. Here is the Peekskill meteorite, the first in recorded history to damage a car, and quite seriously. During its fall, it struck the trunk of a vehicle. A photo of the damaged car is included in the exhibit. Naturally, this story made headlines around the world. The car was eventually sold. The proceeds were enough to buy a new one and still have some money left over. Next, we have the Sterlitamak meteorite, which fell in 1990. It landed in a field not far from the city of Sterlitamak. At the time, there were serious discussions about declaring the meteorite a national treasure of Bashkortostan. Officials began considering how best to manage this sudden windfall. It is, indeed, an interesting meteorite. Its impact created a crater about 10 meters in diameter, which was later excavated, resulting in a pit nearly 25 meters across. Yet, the meteorite itself was not initially found. Ironically, it was discovered the following year by the son of an excavator operator, who spotted it among the spoil heaps. The Borodino meteorite is fairly well known. It fell in the vicinity of the Russian army's encampment shortly before the Battle of Borodino during Napoleon's 1812 invasion of Russia. The meteorite was retrieved and handed over to the command, and it was widely regarded as a favorable omen ahead of the impending battle. Pallas Iron, also known as the Krasnoyarsk meteorite, is one of the most famous in meteorite science. It marked the beginning of meteoritics in Russia. It was discovered and described by Peter Simon Pallas, and became the first meteorite ever recognized as such. It also turned out to be a pallasite, a rare and striking type of Stony-iron meteorite. While working in the Volgograd region, where Pallas studied Lake Elton, he left such a legacy that a nearby town was named Pallasovka in his honor. Near this town, another pallasite was later discovered, which was consequently named Pallasovka as well. Among our specimens is also Lazarev, a meteorite retrieved in Antarctica, the first Antarctic iron meteorite found during one of the Soviet expeditions to the continent. A particularly unusual find is the Clipperton meteorite. It is likely the only meteorite not named after a geographical location or settlement, but rather after an underwater fault zone. While trawling near the Clipperton fracture zone, a ship recovered seafloor sediments, among which a meteorite fragment was discovered. The Chinga meteorite, found in Tuva, was first identified by gold prospectors, who came across metallic fragments of puzzling appearance while panning in mountain streams. It was later confirmed to be an ataxite, an iron meteorite with very high nickel content. In more recent years, a statue known as the Iron Buddha, or Iron Man, resurfaced in a private collection. The artifact had been confiscated by the German Ahnenerbe expedition in 1938 from a Tibetan monastery. It was suspected to be of meteoritic origin and was subsequently examined at the Natural History Museum in Vienna. Analyses confirmed that the statue had been carved from the Chinga meteorite. It is a bas-relief sculpture preserving roughly half of the original meteorite, weighing about 9 kilograms. When and how the statue was made remains unknown, as no reliable dating has yet been conducted. Whether it is a relatively recent object or evidence that Chinga was known in antiquity remains a mystery. The Ivanovka meteorite, a chondrite discovered in Tatarstan, is notable for an unusual story. Only 2 individual fragments were found, about 4 kilometers apart. However, both were discovered by the same person, 10 years apart. He found the first as a child, and the second as an adult working as a tractor operator in the fields. An incredible coincidence. As for the Tsarev meteorite, its discovery is equally remarkable. In 1967, the Soviet Meteorite Committee received a message from a tractor driver. "I have about 4 tons of meteorites." Renowned Soviet scientist Roman Kotinik traveled to investigate, and to his amazement, found enormous blocks of meteoritic material stacked in the man's yard. It was indeed a genuine meteorite, and a truck had to be dispatched to transport the mass. The Kaunas meteorite, another fall in Tatarstan near the Bashkortostan border, occurred in 1937. It caused significant alarm due to a powerful explosion and was one of the largest observed meteorite falls in the region. A local woman harvesting hay reportedly had a 50 kilograms meteorite land just a few meters away from her. Of course, a crown jewel of the collection remains the Sikhote-Alin meteorite, an enormous fall estimated to have yielded between 50 and 100 tons of material. Luckily, it occurred deep in the remote taiga, causing no casualties or structural damage. Nevertheless, the fall made international headlines. Artist Medvedev, an eyewitness, even created 2 paintings depicting the event. On one of the paintings, the Sikhote-Alin meteorite is shown falling from left to right. On the other, with the same background from a different angle. A few words should certainly be said about the American meteorite Canyon Diablo, associated with the famous Beringer crater in Arizona. It is often questioned, there's a massive hole, so where is the meteorite? Maybe it was just an explosion, but in fact, this was a meteorite impact. The bulk of the meteorite was destroyed upon impact, but fragments of the Canyon Diablo meteorite have been found scattered over a vast area, with a radius of about 10 to 12 kilometers around the crater. They can still be found today. The history of this meteorite is notable for Daniel Beringer, who first correctly identified the crater as meteoritic in origin. At the time, however, the physics of impact events was poorly understood. Beringer believed the main mass of the meteorite still lay intact beneath the crater floor, representing a massive iron-nickel resource that could make him wealthy. He invested heavily in drilling operations, which ultimately yielded no returns, as the material had been vaporized or ejected during the explosion. His company went bankrupt, but the land remained in his family's possession, and meteorite collecting there is still forbidden. A few words about the Boguslavka meteorite. This is a coarse-structured hexahedrite iron meteorite, consisting of two clearly fractured crystals. The separation line between them is clean, essentially forming a natural split. Now, regarding pallasites, we have several remarkable specimens on display. For instance, the Esquel meteorite was found in Argentina in 1951. According to records, it was simply lying in the backyard of a house purchased by a local resident. The Brahin meteorite comes from Gomel Oblast, Belarus. Its discovery dates back to 1807, and the region has yielded numerous specimens, making it one of the largest pallasite falls in the former Soviet Union. Another exceptional specimen is the Omelon meteorite. Its discovery is surrounded by a somewhat mythical tale. A reindeer herder reportedly witnessed a fall in the tundra and found a 250-kilogram stone. It had fractured upon impact, with abundant olivine crystals spilling out. The specimen is extremely fresh, with a well-preserved, black fusion crust and no visible rust. Later, other stories emerged. Perhaps the fall wasn't actually observed, and the stone was found accidentally. Then some local people became interested in this stone and almost took the stone away from him, but apparently, the fall was not observed. The Novo-Urei meteorite is particularly important for containing diamonds, making it the type specimen for ureilites. Ureilites are known for their high carbon content, including up to 5% carbon and 2.5% diamond. These diamonds are not gem quality, they are black, microcrystalline, and very hard. Such material is extremely difficult to cut and polish due to the diamond inclusions, which scratch other surfaces. The fall of Novo-Urei provided the name for this meteorite class. In a smaller display case nearby, lunar and Martian meteorites are shown. Martian meteorites are collectively referred to as SNC meteorites, an acronym for Shergotites, Knocklites, Chassignites. Though other Martian meteorites exist, such as Lurzolytic Shergotites, which are yellow in color, orthopyroxenites, and exceptional specimens like Black Beauty, a dark, fine-grained rock, these do not form well-defined groups. They are unique, known from only a single specimen, and classified as anomalous. Thus, when referring to Martian meteorites, the SNC group is generally used as the primary classification. In fact, meteoritic matter does not typically possess any extraordinary properties, except, perhaps, in abrites, where certain areas exhibit fluorescence under ultraviolet (UV) light. For instance, in Norden County, although the sample is embedded in resin, individual spots still glow with a yellowish tint under UV illumination. The same phenomenon can be observed in the Peña Blanca spring meteorite, also an abrite. Although the sample is displayed behind glass and sealed in polyethylene, one can clearly see certain regions brighten under UV exposure. Our exhibit also includes a sample of lunar soil returned by Luna 16 from the Mare Fecunditatis, Sea of Fertility. This small heap of gray dust is actual lunar regolith, just as it exists on the moon. There's a recurring misconception that regolith is glass. But as you can see for yourself, it is ordinary dust mixed with fine-grained fragments of rocky material. The question of whether the Americans actually landed on the moon and brought back lunar samples still arises frequently. What can be said in response? Well, high-resolution imaging of the lunar surface has now been conducted. You can look at the Apollo landing sites for yourself and decide, were they there or not? Everything is clearly visible. There are also large individual specimens of the Tsarev meteorite, previously mentioned, so massive they had to be transported by truck. An interesting story is associated with the Timochin meteorite. In 1967, during a geological survey, a geologist found a sizable iron mass, approximately 250 kilograms, which was submitted to the Meteorite Committee and identified as an iron meteorite with silicate inclusions. Specialist Svetkov flew to the site, and while the meteorite was being loaded, he used a basic metal detector to locate a second specimen, weighing around 50 kilograms. Both were collected and subsequently forgotten. However, in 2004, a search team unexpectedly found several additional fragments. Upon cutting into one of them, it was revealed not to be just iron, but a pallasite, and a particularly beautiful one at that. Thus, the story took on a new chapter. There is an absolutely remarkable specimen of the Sikhote-Alin meteorite in our collection. A common question asked by visitors is, what are regoliths? Regoliths are the thumbprint-like depressions seen clearly on this meteorite's surface. Generally, stone meteorites do not exhibit regoliths. However, as we've seen earlier, some oriented stony meteorites do feature regoliths despite their composition. Finally, I would like to say a few words about the internal structure of iron meteorites. The Widmanstätten pattern, or Widmanstätten figures, is fairly well known. Its geometry, appearance, and formation are well studied. This is the distinctive structural feature we refer to as the Widmanstätten pattern. People often comment, this one doesn't etch. It's an ataxite, just gray, and nothing more. But in fact, one can observe the structure of an ataxite quite clearly. It's just that this structure is microscopic in nature. The waves and surface ripples visible on this sample actually consist of microscopic cross-hatched patterns, which become readily apparent under a stereo microscope or binocular loupe. As meteorites fall, they frequently experience tremendous mechanical stresses, which can cause them to fracture, shatter, or break into fragments. Naturally, such intense impacts lead to structural deformation, and this is often quite evident upon etching the specimen. In fact, by studying the etched pattern, one can often determine which side of the meteorite struck the ground and where it bent or fractured during impact. Etching is typically performed using a solution of nitric acid in ethanol, known as nitol, which enables clear visualization of the Widmanstätten pattern. Various etching methods exist, and they can even be used to produce aesthetic coloration effects. For example, black etching highlights the structural features in stark contrast, making it particularly suitable for demonstration or display purposes. Another technique is colored etching, which is not a result of oxidation but rather a chemical treatment that stains different kamacite lamellae in varied hues, producing a visually striking pattern. An unusual structure is also seen in this pallasite sample, but here the olivine crystals are extremely small and evenly dispersed throughout the matrix. This is also a Timochin meteorite, albeit a very atypical specimen. What makes it especially interesting is the uniform distribution of metal and olivine. There are no large olivine crystals, nor are there distinct metallic veins. The structure is finely textured and homogeneous. One of the most beautiful pallasites known as Imilak, notable for its highly transparent olivine crystals, which are widely regarded as some of the most visually striking and aesthetically refined among all meteorites.